So let's test this one for convergence. Okay, so the n part of this series is 1 over n, and the power series part looks like that. Okay, so we're going to do our ratio test. Okay, so we're going to do our ratio test to find the radius. So the limit as n goes to infinity, okay, we're going to end up with 3x to the power 2n plus 2. Okay, and then we're going to end up with n plus 1. All divided by 3x to the 2n over n. And apply our ratio. We don't want to know where that is less than 1. Okay, so again, group your terms. We can group together our power series part. So we're going to end up with 3x to the power 2n plus 2 divided by 3x to the power 2n. We end up with 3x to the power 2. Okay, so there's our power series part. And then for the sequence part, we end up with n over n plus 1. And again, we want to know where this is going to go, where this is the limit of this when n goes to infinity, and we want to know when it's less than 1. So when we work this out, this portion here becomes 1. So the limit of n over n plus 1 over as n goes to infinity is equal to 1. So we end up with 3, I'm just going to write this as 9x squared. 9x squared, okay, is less than 1. So the center is at 0. So I want to see my radius a little bit easier. So I'm just going to divide both sides by 9. And so I know it looks like my radius is going to be, well, my x squared radius is 1/9. So my x radius, we know that the x is going to be less than 1/3 and bigger than 1/3. Okay, so we need to solve that inequality for x squared. So at this point, we know this is our radius. Okay, so we have a radius of 1/3 centered at 0. Okay, once we establish that, we need to test our endpoints. Okay, so we're going to test endpoints. Okay, so we're going to test x equals negative 1/3. Okay, so what happens when we plug that in? Okay, when we plug negative 1/3 into here, this is our series. We end up with negative 1 to the 2n. Well, 2n is always going to be even power, so that's always going to be a positive. Okay, so we end up with this is not an alternating series, it's a harmonic series, so it's divergent. Okay, so I'm just going to simplify this. This is all just going to end up being 1 over n, divergent, because this is our harmonic series. Okay, so the endpoint then, we are not going to include the negative 1/3. Okay, so we're just going to make that bigger than negative 1/3, not equal to. So then we need to test the other endpoint of positive 1/3. Okay, so when x is equal to positive 1/3, when we plug that in, we're going to end up with the series from n equals 0 to infinity. This is going to be 1 to the 2n over n. Again, this is divergent. Again, same reason. It's a harmonic series. Okay. Okay, so we can then not include this endpoint here. Okay, so then our interval of convergence, I'm just going to use black here. So interval of convergence is going to be from negative 1/3, not including, to positive 1/3, not including. Okay, so whatever function this mimics, it's only going to be good in that interval, and it'll do a good job in that interval, but once we get outside that interval, it's no good. Okay, so let's try this one. This one has the sequence part of it is a Basel series, or P series power 2. Okay, so let's set this up. We need to, again, first of all, set up our ratio test to work out the radius of convergence. So the ratio test is going to give us x minus 3, 2n plus 2 over n plus 1 squared all over x minus 3 to the 2n over n squared. Okay, again, we want to know where this ratio is going to be less than 1 for what values of x when n goes infinite. So rearranging this then, limit as n goes to infinity. Okay, so the power series part of it cancels out, so we're just going to be left with x minus 3 to the 2n, to the power 2. When all that cancels, we're going to have 2n canceling the 2n, so just plus 2. And for the sequence part of it, we're going to end up with n squared over n plus 1 squared is less than 1. Well, what's going to happen here is that we know that this sequence, this series here, when n, this is just going to be a quadratic over quadratic as n goes to infinity. Well, we know that's equally strong, so we end up with a limit of 1. So we end up with x minus 3 squared is going to be less than 1. Okay. So our radius in this case, we can get rid of the squared because that's 1. We can then, our radius is going to be 1. Our center is going to be at 3. So our interval is going to be from, looks like it's going to be 2 to 4. Okay, just plugging in, yeah, 2 squared, negative 1 squared, yeah. Okay, so it's going to be looking like that. So we've established our radius. Now we have to test our endpoints to determine the interval of convergence. Okay, so our test the endpoints. Okay, x equals 2. We plug it back into our expression from n equals 0 to infinity. Okay, when n equals 2, we're going to have negative 1 to the 2n. Well, 2n is always even, so that's going to be a positive numerator over n squared. So when we work out this is going to be an basal series or p series where p is greater than 1. So this is convergent. Okay. So we're going to include this endpoint of 2. So less than or equal to. Okay, we test the other endpoint. X equals 4. When x equals 4, we're going to end up with, it's going to be 1 to the power 2n over n squared. Okay, again, this is a basal series or p series greater than, where p is greater than 1. This is convergent. Okay, so then we can include that endpoint. Okay, so then we can make our final conclusion here. Our interval of convergence is going to be including 2 and including 4 as our endpoints. So this is what we would call a closed interval.